Progress.
All right, everyone. In this video, we are going to learn about a numerical technique for approximating a solution to a certain kind of differential equation. And this technique is called Euler's method. I'll briefly just mention here, notice that the way this is spelled, it looks like it should be called Euler's method, but this is a mathematician whose name was pronounced as Euler, and it's an easy mistake to make. So I would just, yeah, wanted to mention that. Euler's method, the mathematician Euler. So again, this is going to be a method for approximating a solution to specifically a first order differential equation that can be graphed using a slope field. So the example we'll be looking at is this slope field given by the differential equation dy dx, or y prime, is equal to x plus y. And when looking at a slope field like this and trying to approximate a given solution, we will often want to start at a specific point, and then what we have discussed previously is that we would like to sort of kind of flow through the slope field, trying to follow the little directed line segments as best as possible. Euler's method gives us a strategy for doing this, and the idea is listed on the, or is identified on the right of the screen. So the idea is that we're going to start at a given starting point, x comma y. And in this example, we will start at 0, 0. So we're starting at the point 0, 0. Just draw that here. So starting at the point 0, 0. At the given point we are at, we will calculate the dy dx using the differential equation, and this determines our trajectory, our sort of angle of direction. So in this example, because we're at the point 0, 0, I'll point out that what this means is that the slope dy dx equals 0. This is because we're using the boxed equation up here, dy dx equals x plus y. So at 0, 0, this is 0 plus 0. So we just get 0. And that means that at the point 0, 0, our line segment extending from that point would be perfectly flat. All right, it would have a slope of 0. So that is our trajectory, this sort of flat trajectory going this way. Now, this next step allows us to actually start graphing our approximate solution. We are going to take that point and take that trajectory and go a fixed distance forward to a new point, x comma y. So this fixed distance here, this is a given, I'm going to call it a step size. And it's specifically a distance in the x direction. So for this example, we're just going to use a step size of 1 to keep it easy, which means that I'm going to take one full step forward in the x direction. So I started at x equals 0 down here. I'll end up at x equals 1. And because my trajectory is flat, I will draw this flat line all the way to the point 1, 0. And this is our new point. So we went a fixed distance forward with a step size of 1. So we went 1 unit forward, and we got to a new point, and this new point was the point 1, 0. Now you'll notice in order to get that far ahead, I had to cut across several lines that were starting to slope up, and that is okay. In Euler's method, the starting point that I'm at determines my trajectory, and then I keep that trajectory for the entire step size. So even though the little line segments in the slope field started to curve up, I maintained that flat trajectory until I finished my step and made it to my new point. And my new point was the point 1, 0. And so this is the first sort of big step in Euler's method. And now we are just going to repeat this process many times. So I'm at a new point now. I'm at the point 1, 0. And let's see what we get. So at the point 1, 0, I would calculate a new dy dx. And at this point, This new point I'm at, dy dx, is x plus y, so that's 1 plus 0, so that's just equal to 1. And notice at this point, we have what is essentially a line segment with a slope of 1. Because of the aspect ratio, it doesn't actually look, it looks a little bit shallower than we might expect, but that's because of the aspect ratio of this picture. It should be 1 unit over to 1 unit up. And in fact, that actually determines our trajectory. We will now march 1 unit over, so getting to an x value of 2, and with a slope of 1, we're going to get 1 unit up. So that's going towards the point 2 comma 1. I'm just sort of visually IDing it there to make sure that my picture stays semi-clean. And now this is supposed to be a nice straight line from our old point to our new point, and our new point is the point 2 comma 1. And let's repeat. Let's do it one more time. So at the now point 2 comma 1, we need to calculate our slope one more time. Our slope at that point is given by dy dx equals x plus y. So dy dx equals 2 plus 1. So dy dx equals 3. And this means we will have a slope of 3, which means that every time we take 1 step over, we're taking 3 steps up. And indeed, that's exactly what we're going to do. So our new point would take 1 step to the right and 3 steps up, and we would get to the point 3 comma 4. And now this is actually off of our page, but taking 1 step to the right, we would take 3 steps up. We'd get to a height of 4, which seems to be maybe right about here, just sort of eyeballing it. And let me grab, I'm going to try to draw this straight line. Okay, good enough. So I'm going to get this nice straight line here. And maybe this is my stopping point for this example. So again, we started at the point 0, 0. The flat trajectory and 1 step forward took us to the point 1, 0. Our new trajectory and 1 step forward took us to the point 2, 1. And then our newest trajectory and 1 step forward took us up to the point 3, 4. But you could imagine repeating this as far out as we wanted. I'm going to scroll down the page here, and we'll see that I've actually gotten a computer to do this for me. So here is my example of that. You'll also notice this computer system, when I entered the initial value of 0, 0, it backward propagated this as well. So I was able to get a full picture of this here. Okay, cool. So this is Euler's method. It gives us a way to systematically and algorithmically approximate what might be a solution by following along with these directed line segments. And the key here is that there is this constant step size going forward. In our example, it was a step size of 1. So as I marched from one point to the next, I would take a full step forward in the x direction. And then, of course, my change in height, how far I went up or down, was depending on that trajectory we had calculated earlier. Now, clearly, though, this example is not following these directed line segments that well, and so it's really a rough approximation. Think of an early picture of a Riemann sum with some really big rectangles. It's an approximation, but it's a bad approximation. How might we improve this? Well, thinking like Riemann sums, we might make our approximating objects a little bit smaller. And so in this example, the key to making a better approximation is to decrease that step size. Make sure that we're not taking a full unit step every single time forward in the x direction, but make it something a little bit smaller. This will give us more times to pause and readjust our trajectory based on the new point we're at. And I'm going to scroll down, and we're going to see that we have done that. So we can shrink the step size. Here's an example where the step size is 0.5. So we went 0.5 units over. This is the same slope field, of course. but 0.5 units over. So this is an x value of 0.5. This is an x value of 1. Let me see. And so tracing up, we get to 1. We readjust. This is a step size of 0.5. So now we're up to 1.5. We readjust, go again, and go again, and so on and so on. So you can see how we are constantly readjusting. Whoops. Constantly readjusting every 0.5 units forward that we go. And making our step size even smaller will give us an even better approximation. So I'll conclude this video by looking at a step size of 0.1. This means, of course, that there are 10 different breaks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 different breaks between 0 and 1. And so what looks like a smooth curve is really a bunch of teeny tiny straight line segments. Each time we're readjusting the trajectory and drawing the next line segment. And at this point, it is indistinguishable from a smooth curve and gives us a very strong sense of what a good approximate solution would be. So there is an interesting trade-off here where to get a better numerical approximation, we need to make our step size smaller, but that would increase the number of computations we would need to do, right? We would need to do 10 computations just to get to this point right here. Whereas in our very first example, going 1 unit out in the x direction, it was just 1 computation. So there's an interesting trade-off between accuracy and computing power. And there's also this question of how we keep all this information organized, but we'll save those conversations for another time. Thanks so much for watching, and see you all next time.